Hello and welcome to the Gestalt IT Rundown for July the 6th, 2022. My name is Tom Hollingsworth and I want to wish everyone out there a happy International Kissing Day. That's right. This is going to be one of the best rundowns that we have all year because joining me once again is my co-host and my partner in crime, Mr. Stephen Foskett. Stephen, welcome to the show.
Hey, it's good to be here. It's not International Kiss Day, right?
No, it's not, because if it was, we'd be showing up in face paint. Of course, I would be the demon and you would be Peter Criss, because that's just how we roll. But we do have a great lineup of news stories coming your way that we're definitely going to want to dive into. And the first one is kind of a big, well, small story because Samsung announced this week that their long development process for their 3 nanometer chip production has finally started producing. The tiny manufacturing technique uses something called gate-all-around transistor technology, which is appropriately acronymed GAFET, and is a way to keep pace with the chip giant TSMC as well as a few other companies. Now, the initial yields that are coming from the line are going to be targeted at high performance, low power computing, but not mobile chipsets, because those are going to come a little bit later once they've gotten the manufacturing process nailed down and probably even moved on to a different process node in that whole lineup. This is probably aimed by a lot of executives at Samsung to help recapture some of the chip market, because some of the people that are supplying their chips, like Qualcomm, have actually gone to TSMC to get the processing done because TSMC is seen as a leader. But there is still the opportunity for Samsung to catch up in this chip market. Stephen, is 3 nanometer process a big deal, or is it really just small potatoes?
Yeah, I'd say that this is overall probably not as impactful a story as you might think, because this is very early in terms of actually bringing this stuff to market. Samsung is not saying that they're basically ready to start manufacturing this way, but they are saying that they've gotten it to work, which is important because gate all around is, as you mentioned, that technology is what's going to enable us to move to the next generation of chip density. Intel and TSMC are both working on gate all around technology, and both of them expect that this technology is going to allow them to deliver on the next generation promise. It's important to remember, too, that for a while now, we've actually moved away from the actual nanometer scale production. And in fact, most companies are now using basically 10 nanometer to produce these 5, 6, 4, 3 nanometer items, because essentially what they're doing is they're figuring out better ways to use the space internally without actually having to shrink the actual size of the features. Gate all around, as you said, is the sort of the next generation here. They moved from basically planar to thin, which literally like puts the thing up vertical, to gate all around, which basically allows more verticalization of the features. The next generation we're going to see here is a technology called nanosheet, which is another way to improve on the gate all around technology and allow you to pack more and more and more and more in at higher and higher power levels with reduced cooling needs. And so all of this is positive. It kind of goes toward the Intel story that we mentioned recently, where Intel is starting with their Intel 4 process. TSMC is working on this, and everyone's trying to basically pack more into the chips. I think the cool takeaway from this is that it's not a one-horse race. It's not TSMC way out ahead of everybody. In fact, it's at least a 3-horse race. We've got TSMC, Samsung, and Intel all actively investing, all iterating, all developing next-generation technologies. And quite frankly, that's good news for everyone. So, Tom, we've talked a little bit about Swimlane before, and security automation platform announced this week that they've closed a new funding round at $70 million. The highlight of the campaign was their focus on how code automation and it could be used as a force multiplier for organizations that are facing staffing issues, which is frankly a lot of them now. Instead of putting all the features into a security automation orchestration and response platform, Swimlane focuses on providing just enough software at the right locations to solve security challenges. And we saw this actually at our Security Field Day event last year. Is this a better option for companies than a massive new system?
Well, you run into a couple of different problems here. So everyone went out and bought a security incident and event manager, a SIEM, and then they bought a SOAR, and then they bought an XDR, and then an EDR, and a PQR, and an XYZ, and yeah, it's security, so it's filled with acronyms. But the problem is, just like every other issue that you've ever had, you have all these systems, but you don't have any glue to pull them together. And that's effectively what Swimlane is doing. In fact, during Security Field Day, one of our delegates brilliantly pointed out, you guys are basically the plumbing for all of these devices that pulls the information along the way. But more importantly, it's the plumbing that works without needing to know like Go or Rust or Python or I don't know, Fortran. They use a system very similar to what Ansible does with these playbooks, where you create an automation code booklet, if you will, and you deploy it, and it allows you to connect systems into these devices. And you're probably thinking to yourself, oh, that's really easy. Like all I have to do is tell my device to send all my syslogs to the SIEM or the SOAR, and it all works. Go on. Let me know how that works out for you. Because these companies that sell these huge devices, these huge platforms, there's a reason why they have professional services departments. Because it turns out these things are actually not that easy to deploy. And the other issue is it's a lot like buying a gigantic SUV or buying one of those refrigerators that has like 47 options on it. You're going to keep using this thing for a long time. Like this isn't just something you buy, use for a year, and then go, nah, it didn't really do what I wanted it to do. So I'm going to move on to the next thing. And that's where I think the brilliance of Swimlane comes in. By having these customizable playbooks that you can deploy through their Turbine platform, you can actually just keep adding pieces and connecting them all together so that you can leverage those investments. And it was obviously good enough that they got a $70 million funding round. So I expect to see good things coming out of them very soon. And we hope to get them back to a future security field day very soon so you can hear a little bit more about some of the stuff that they've been working on. All right, Stephen. We all know who FedEx is. They are one of the largest delivery manufacturing or delivery companies on the planet. But now they're delivering, well, nothing except change because they are announcing this week that they are going to be shutting down all of their data centers by the end of 2024. And they are going to be retiring all of their mainframe computers. And what are they going to do? That's right. They're delivering right to the cloud. FedEx built their first data center in 2008 in Colorado, and pretty soon they expanded into Tennessee and had been operating both of those data centers. There was plans to open a third one, but those never actually came to fruition. But a few years ago, they actually, back in 2019, announced that they were going to have Switch, the SuperNAP, in Las Vegas, hosting their entire Western U.S. data center. And today we find out they're actually going to be shutting everything down. They're going to be retiring all of that stuff, and they're going to be moving everything into Microsoft Azure and Oracle Cloud. Now, the funny thing is that that partnership with Switch actually developed into something with IBM where they were going to be opening all of these edge data centers. So why did FedEx decide to start going to the cloud instead of doing all this on-premises stuff, Stephen?
Yeah, I don't have any specific insight into the FedEx story, but I will say that our regular listeners are going to say, wow, this sounds like a familiar refrain, doesn't it? A big old school company with lots of mainframes and on premises stuff wanting to move to the cloud. And frankly, many of these companies, many of these projects are more hot air than they are actual results because a company, just because somebody says we're going to move to the cloud in 2 years doesn't mean it's going to happen. Also, I think that history teaches us that it's really, really hard to get off the mainframe. FedEx is predominantly a mainframe company. It's one of those kind of old school logistics companies like the airlines and so on that have really, really optimized mainframe systems, making sure that everything works. And as we've seen with airlines, getting off the mainframe may sound like an easy task, but it's actually so difficult that we recently, a few years ago, saw Continental and United merge mainly so that United could move from a 40-year-old mainframe to a 20-year-old mainframe solution for scheduling. The idea that FedEx would be able to ditch all their mainframes and ditch all their data centers in 2 years and save $400 million sounds like the kind of thing that you hear from the sort of MBA CIO types who aren't really aware of the challenges of implementing technology. So, again, I don't want to throw any stones because maybe FedEx is amazing and maybe they're going to actually do this. But I'm going to basically say that if you hear a CIO say we're ditching on premises data centers, or even worse, on premise data centers, and you hear them say we're going to ditch the mainframe, we're going to go all cloud, we're going to be all Oracle and Azure and whatever, and move to the edge and all this, and we're going to save all this money in 2 years, it ain't going to happen. Generally speaking. So, best of luck to you, FedEx staff. I hope this works out for you. And I hope that the FedEx IT staff isn't running for the door after hearing that this is supposed to happen in 2 years and save a ton of money. Tom, we're definitely living in the future because Airbus, along with several European space agencies, have released a paper detailing items that need to be addressed in order to keep satellites safe from cyber threats. This paper is a very comprehensive list, and not only the satellites during the design phase, but through construction, as well as securing their networks in space and allowing them to communicate. There's even a section on how to properly retire the devices and keep them from being compromised after their shutdown, which, of course, anyone who's watched Cowboy Bebop knows all about. Tom, is there a growing market for out of this world security?
You wouldn't think that, but we learned something in this year that it turns out that satellites are just as big a target for certain kinds of operations as anything else. There were stories coming out of the conflict that's currently going on in Europe that Russia was targeting satellites that were providing intelligence or communications capabilities to the Ukrainian forces on the ground, doing things like hitting them with high burst radio transmissions, using lasers in an attempt to burn out their cameras. Like, you would think that's crazy, right? Well, wasn't that long ago that the idea of having a Cray supercomputer in your pocket that can take wonderful pictures was not that, it was a pretty far-fetched idea too. I love this paper. There's not like a step-by-step process for, like, how to keep your satellite from being hacked, but it's a list of things that you need to take into account. And some of these things you would never think about. For example, what do you do with the hard drives on a satellite? Do you wipe them? Is there a way to wipe them? Do you wipe them when you move the satellite into a parking orbit where there's like a graveyard orbit is the term that they use? Or is it better for you to try to crash into Point Nemo in the ocean and hope that the satellite burns up on reentry? What if it doesn't? Like, you have to have all of these contingency plans. And it sounds crazy. Like, you would think, oh, well, somebody has planned for this. No, remember that these are devices that are designed to work under the most extreme circumstances. And if you want proof of that, we can still talk to Voyager 2. That satellite is 45 years old, and we still talk to it, and we can still make things work on it. If you are worried about how people might be able to recover information from your devices long after they've been parked in a relatively stable orbit, you need to read this paper. I think you should read it anyway. It's in German, so you're going to have to find somebody to translate it for you. But it's kind of fascinating to think about some of the things we don't normally think about when we're doing communication stuff in a network. It's like, oh yeah, the hard drive died again. Well, what if the hard drive's designed to never die? There you go.
Hey, Tom, let's turn the page here and take a little bit of a deep dive into a story that could, in the future, be pretty important. NIST has announced their selection for quantum safe encryption algorithms. This competition has been running since 2016, and we've been reporting on it here on the Gestalt IT Rundown ever since. The standards body realized that quantum computing could potentially impact some aspects of RSA based public key encryption. The new encryption method that's been selected is called Crystals Kyber, as well as digital signature methods named Crystals Dilithium, Falcon, and Sphinx Plus. And all of them are designed to be implemented in the coming years for highly sensitive data that could theoretically come under attack from an advanced threat from a quantum computer, as well as the inevitable future of computing development. Tom, are we all going to have to get new tokens?
Well, it depends. Which is obviously the IT answer. And part of the reason why is because the impact of what we can do with a quantum computer on traditional encryption algorithms is still very kind of unknown at this point. And we talked a little bit about some of this back in 2020. I had just recorded an episode talking about quantum computing and quantum safe encryption. And effectively, the Cliff's Notes version is the reason why modern encryption algorithms work so well is because effectively they're doing math problems that take so long to solve that by the time you solve the problem, the data is useless. And we're talking about factoring large prime numbers and using the results of the math operations to create a key that's used to encrypt data, right? Sounds pretty simple in theory, although the math behind it's actually really hard. Well, it turns out that with a quantum computer, with a sufficiently powerful enough quantum computer, you can create an operation that will effectively solve all possible factors for a number in a very short amount of time. And when I say a very short amount of time, I'm still talking about hours or days as opposed to years or eons. And so that's what people are worried about, because with a powerful enough quantum computer with enough data, you can effectively crack encryption in virtual real time in a matter of hours or days. And that's what have people worried. Now, all the way back in 2015 and 2016, the US government said, we've got to fix this problem before it actually causes us to lose all of our data. Because, like AI, once the genie's out of the bottle, you can't put it back in. Now all of the encryption is invalidated. And if you're asking yourself, well, doesn't this sound an awful lot like Sneakers, that movie that they made in 93? Yeah, Alderman, the A in RSA, was a technical advisor on that movie. So the stuff that they did, while farcical, is actually mathematically accurate, just way early, because it's been 30 years and we still haven't built one of these computers. But it's important that we have these algorithms now, because it means we can start implementing them so that when the inevitable comes, we don't have to worry about re-encrypting a whole bunch of old data or changing out a whole bunch of old security signature algorithms, because that's going to be a massive undertaking. Think Y2K, but secretive. Now, Stephen, you dug into some of the technical details on this, and I'm kind of curious to see kind of what you came up with.
Yeah. And let's sort of reduce this a little bit, I think, to help understand what's going on here. I think it's important, number one, to point out that quantum computers currently actually don't do this. They theoretically could, and that's the important part. There's an algorithm called Shor's algorithm that would theoretically allow quantum computers to do some things that are currently really hard and time consuming extremely quickly. And I think that that's the real risk, is that at some point in the future, quantum computers could be developed that could attack the mathematical problems that underlie what's called the trapdoor function of a encryption algorithm. So here's the thing. As you can imagine, if we use the metaphor of like a door lock, if you have the key, it's easy to open the lock because the lock is made for the key. It's kind of the same with encryption. The lock is made for the key in that we know which primes we used, so we can use that in order to solve the problem quickly. The reason we do this, and the reason that we have these challenging mathematical problems built into cryptography, is because of time. Essentially, what you want is you want to make it take long enough, as you mentioned, Tom, to try all the keys, that you can't practically try all the keys, because otherwise you could, right? I mean, you could either build a giant rainbow table or have a bazillion core computer, or frankly, a quantum computer with Shor's algorithm hitting every key at once. And if you can do that, if you can go through all the keys, well, then of course you can open all the doors, because essentially, I mean, imagine if you're that guy in the movie, right? Except your key that you stick in there is literally every possible key, and you turn it, and of course one of them works. That's basically what Shor's algorithm says is theoretically possible with quantum computers, because the keys that we're talking about are basically solving three hard mathematical problems. You've got integer factorization, you've got discrete logarithms, and you've got elliptic curve discrete logarithms. And all of these things are things that are extremely difficult and time consuming for regular computers to do. So effectively, having these be the problems that underlie cryptography means that with all conventional computers, it's going to take so long that, as you say, it's just not practical to try to guess the key. But with quantum, theoretically, you could guess all the keys at once, or at least something along that lines, and solve the problem in a reasonable amount of time, which means suddenly cryptography doesn't work anymore. So the key here, what's really going on here, is that we've got this new algorithm that's going to replace the trapdoor function. And that new algorithm is based on a concept called learning with errors, which sounds comedic, doesn't it? But essentially, it's a machine learning challenge. And as you may know, machine learning is all about matrix math and essentially going through and calculating all the answers to given a whole bunch of different variables. You count all the answers and then you kind of build on that and build on that. Well, without getting too far into it, because frankly, I don't understand it all that well, but I've tried. And essentially, this whole concept of learning with errors is something that requires you to go through all these iterations. And a quantum computer just can't shortcut. It can't try all the problems because it can't, because they build on each other. And because of that, theoretically, Kyber and crystals and all that, it might be, it probably is quantum resistant. But I think there's a couple things that people need to keep in mind here. As I said, number one, this is all theoretical because no quantum computer can do this that we know of at this point. Number two, the math says that quantum computers probably won't be able to do this. But of course, we don't really know that either because we kind of don't have them. I mean, it's all theoretical. And then number three, everybody's immediately going to jump to, oh, the NSA has compromised NIST and this is blah, 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 and there's secret backdoors and all that kind of stuff. And you know what? We can't guarantee that there aren't. Hopefully there aren't. But it's entirely possible that all of this is a complex ruse or a good excuse for NIST to compromise encryption again, which they did before, and that's one reason that everybody's really frustrated. But the problem is there's nobody other than NIST that can set cryptographic standards, and so kind of we all in the world kind of have to trust them anyway. I don't know if you've got anything more to say about that aspect, Tom.
Well, actually, I do, because there's a couple of other things you have to keep in mind. So, Stephen, you're absolutely right that that we're working on a theoretical basis right now. You have to have a super powerful quantum computer in order to do this. To give you an idea, the most powerful quantum computers in existence right now are running a little bit over 100 qubits. You don't need to know what a qubit is. Actually, if you do want to know what a qubit is, we'll link an article. We'll link the conversation that I had about this. But effectively, think of a qubit like a gigahertz on a processor. So right now, the most powerful quantum computers are running at a few hundred qubits, like 120. IBM and Google think they can get to a 5,000 qubit computer maybe by the end of next year. You would need a computer in the several millions of qubits in order to be able to decode this stuff in a matter of hours. And that doesn't take into account error correction. It's not just that you have all the gas, you actually need a little bit of brakes. Because with the way that this whole thing works, which again is way too complicated to talk about here, it's not just going fast, it's being able to correct all the errors that you create along the way to be able to figure out all the possible states of the qubit. And we're still not really doing the error correction part right now. We're building really, really fast computers, but they're effectively producing white noise right now. So that's one of the reasons why we're probably thinking that this is going to be a big challenge to solve, is because you not only have to have superpower, but you have to be able to read the results in order to make them make sense. The other thing that I thought was really interesting from this was they interviewed Bruce Schneier, who's a very well-known security researcher, and they asked him about why it took so long for this process to come back. And Bruce effectively said that there were 96 algorithms that were submitted for encryption and digital signatures when the first round was opened up, and they hammered these things. They weren't just testing to see if they were going to be resistant to quantum interference effectively. They were testing them to make sure that they couldn't be accidentally compromised for a whole lot of other reasons. And it's funny because in the last round, there was actually an algorithm called Rainbow that was very popular. And when NIST and their team got a hold of it, they absolutely destroyed Rainbow to the point where not only was it not quantum resistant, it could have actually been compromised by a modern laptop. There was like some kind of factoring thing that was built into it that effectively allowed people to just shortcut right through it. And in the complete honest transparency, Dilithium and Kyber had a similar problem, but not to the degree that Rainbow did, and they were actually able to patch that out so that they were able to select those as the final uh, things. And to talk about the NSA point, yes, now that we know that the NSA has actually been kind of monkeying around with elliptical curve technology, and we've actually had a number of stories about that here on the rundown. Someone actually interviewed somebody from the NSA a couple of months ago, right when this the announcement was made that they had finalized it and they were going to make the announcement soon. And someone went to the NSA and was like, "Hey, are you guys monkeying around with this again?" And cross my heart and hope to die. The NSA says that they didn't do anything this time. Now, I will say that given the amount of testing that these things went through from researchers in the community as opposed to government researchers, I would tend to err on the side of probably this being something that is at least somewhat protected. I hope that I don't have egg on my face in a couple of years when it comes out that it actually wasn't. But the other good thing is that now that we have a baseline to work from, we can actually start developing more amazing, crystal named algorithms like, I don't know, like Mcron or something. But basically, now that we know where we need to go to get this solved, we can start building on what we have as opposed to just hoping that this is going to be enough. Because if you believe that, remember that at one point that we believed that DES was uncrackable. And well, now we're here today where we know absolutely that it totally is. Speaking of where we are today, we are at the end of our Gestalt IT rundown, but we do have an exciting thing coming up later this month. Actually, it's next week that you definitely want to take advantage of. And that's going to be Mobility Field Day. That's happening July 13th through the 15th. I'll be out there with some of my friends from the mobility industry talking about all things related to wireless, which means that next week, Stephen will have a co host to help him out through the rundown. But we hope that you'll be able to tune in and see all the cool things that we've been working on, both here at Gestalt IT as well as Tech Field Day. We have a lot of great content that you will want to take advantage of. We'll be back with you next week at around 12:30 Eastern Time for our rundown. You can always find the latest episode on our YouTube channel at youtube.com/Gestalt IT video. You can also subscribe to us in your favorite podcast application of choice. And if you do that, especially over on iTunes, why don't you leave us a rating and a review so that it helps other people find, our podcast helps learn a little bit about what we're about. We know we have a lot of fans out there who get their enterprise IT news from us and love the little sprinkling of snark that we put on top of it. So that'll just about do it for the Gestalt IT rundown. We hope that you have a great day and an amazing week, and we will see you next time.